All right, so now we're on to nuclear physics. So we're going to do 2 lessons today. The first one is lesson 7, the nucleus. So one thing you need to know about the nucleus is inside of it, we know there's neutrons and protons. These are things that we discovered when we talked about the atom. We call these things nucleons. So when we're talking about neutrons and protons, combine them together, they're categories called nucleons. So we have masses that we're going to be using throughout. There's masses on your formula sheet for both protons and neutrons, and it shows that they're roughly equal in mass. They are equal to a point. If you take a look here, we see that one of them is 1.0073 U, and the other one, neutrons, 1.0087 U. And this U is known as an atomic mass unit. Atomic mass unit. Sometimes you'll see it called AMU for atomic mass unit. These numbers can be found on your data sheet at the back. It's just another way of kind of comparing that to electrons and everything else. Okay, so an atomic mass unit. You also notice on the back of your formula sheet that not only protons and neutrons are written in U's, but sometimes electrons and other things as well. All right, so nuclear notation, kind of similar to in chemistry where we have all these numbers kind of floating around our symbol. In this case here we have A, which is the nucleon numbers. So this is the number of protons and the number of neutrons combined. So in other words, number of nucleons. That's what it states there. Yep. And then Z is the atomic number, which is just the number of protons. And then X would be the symbol. So if we're talking something like helium, you can then say, well, replace that X with HE, and then you can say that this helium we know has 2 protons, and maybe in this case it has 5 nucleons. So this would be the way that we write out our elements. So in this case, we will be needing the periodic table, and I'll see if I can find that and share that with you guys, because for all these questions kind of moving on in this point, in this topics, we will be using the periodic table as a way to help out. All right, so isotopes have the same number of protons, but different number of neutrons. So this helium-5 compared to helium-4, they're both helium. The only difference is they have different number of neutrons. Same element, but they're isotopes of each other. So that's just the terminology we use. There's these things called quarks. They are not fundamental. So it says protons and neutrons are not fundamental because they're made up of something smaller, right? The building blocks of protons are these quarks. So one way I use to remember these is if I draw a little circle, draw another little circle, we can imagine, assuming that protons and neutrons are roughly the same size, they're made up of up and down quarks, a combination of these two. And it turns out that if I were to draw this as an up, and a down, this would be one element, and then the other one would be not element, I'm using the wrong terminology, one particle. So we have a proton and a neutron. And if you look on your formula sheet, you can see that the charge of quarks, they have fractional charges. So if you look at an up quark has a positive 2/3 charge, and it's a positive 2/3 E. Well, a down has a negative 1/3 E. So if you think about the difference between a proton and a neutron, well, we know the proton has an overall positive 1 charge, and a neutron has a neutral charge. So if you look at this and say, well, I have 2 ups and a down, well, that would have a charge of positive 2/3, a positive 2/3, and then a negative 1/3. If you add that up, well, that's 4/3, and minus 1/3, that's 1 over 1. So this has a charge, in this case here, of a positive 1. And not just positive 1, but like I mentioned, a positive 1E. Compare that to the down, down, up. We notice that the downs are negative 1/3 E, negative 1/3 E, so that's 2/3 E, negative 2/3, and a positive 2/3 E. If you add those all together, we end up getting a zero charge. So in this case here, this must be the neutron. So neutron consists of 2 downs and an up, and a proton consists of 2 ups and a down. All right, so let's take a look at this quick example here. It says determine the missing information of the number of protons and neutrons in each nucleus. So it looks like we're missing a symbol there. So let's try to figure this out. So if there's 2, in terms of this, most likely there's going to be a 1, and most likely it's going to be a hydrogen. So if you look at the only one that has a single 1, most likely it's not helium, but I guess technically it could be. So in this case here, we're going to say this thing has 1 proton, it has 1 neutron. So even though it has 2 nucleons, protons and neutrons, you'll see that here it has one of them must be a proton, the other one must be a neutron. So in other words, 1 proton, 1 neutron, because the nucleons is 2. So I would call this thing a 1 slash hydrogen. Okay, 1 hydrogen. All right, so lithium. So if you take a look at your periodic table at lithium, you'll notice that lithium has a charge of 3. So you'll look at the number with lithium is 3. This tells us that there must be 3 protons. And remember, this is the number of nucleons. If 3 of those nucleons are protons, that means the remaining 4 must be... Oh, I think I did something wrong in the last question. I believe this is a 2 hydrogen. I don't know why I put 1. I saw the 1 down below. Okay, so in this case here, this must be a 7 lithium. Okay, where the 7 represents the number of nucleons. All right, so looking at a notation for common particles, for a proton, we're going to use that as a positive P. You'll notice it looking often like that. A neutron, sometimes at N, sometimes we even have a little 0 above it. We talked about quarks. The quarks are either going to be an up quark, or you can also see a down quark. And also, which we'll talk about in a second, there's something called an anti-up or an anti-down. And anti, so we're just going to put a little line above it to show that these are anti-particles. So these are anti-quarks. And we'll talk more about those in our last topic. Alpha particle, we know an alpha particle is this, and it has a 2+ charge, so I'm just going to indicate that with a 2+. Helium nucleus is also the same, 2+. Gamma looks like this. Gamma has no charge. A beta negative an electron, and it turns out that these are one and the same. These are the same. So often we replace beta negative and electrons, we use them kind of interchangeably. A neutrino looks like this, kind of like a fancy V. Beta positive and a positron. So a positron, if you don't know, is the same mass as an electron, but just a positive charge. And we've talked about the idea of an anti-neutrino or an anti-anything. We'll just have a little hat indicated above. So technically, we could have an anti-proton. Technically, we could have an anti-neutron. All of these things could also be antis. And beta positive and positrons are also the same. Quite often, we interchange these terms. We can draw them as a negative B or a negative E or a positive B or positive B. All right, so the strong nuclear force, protons and neutrons bind together by residual strong nuclear force. The strong nuclear force has the following properties. It binds the quarks together within the neutrons and protons. It acts over very short distances, which still strongly attracts over larger distance than the radius of a proton or neutron. So in other words, Why can protons and neutrons sit side by side beside each other inside of a nucleus? And it's because of the strong nuclear force. Without them, it would just be always repulsive, because we know protons and protons sitting side by side would repel one another. Okay, so once again, it overcomes the repulsion of those protons. All right, we're going to skip over mass defect for now. And that is it. So try to do we'll do the mass defect when we do our nuclear fission and fusion unit. So we're going to skip this for now. Skip for now. All right, so this is the end of the first one. I will make the second lesson video in a few seconds here. Okay.